In this lecture 14, we will study the convergence of random variables, focusing on almost sure convergence. Let's just start by considering pointwise convergence. Consider a random sequence X which maps our sample space omega to the space of real valued sequences R upper N defined on a probability space omega script F P. Then each component X sub N defined as the n-th projection P sub N composed with X mapping omega to R is a random variable. There are many possible definitions for the convergence of a sequence of such random variables. One initial idea is to consider X of omega, which is a real valued sequence for each specific outcome omega. And then to think about the limit as n goes to infinity of X sub N of omega for each individual outcome omega. This leads us to the definition of pointwise convergence. A random sequence X mapping omega to R upper N defined on a probability space omega script F P is said to converge pointwise to a random variable X infinity mapping omega to R if for all outcomes omega in the sample space omega we have that the limit as n goes to infinity of X sub N of omega equals X infinity of omega. Now this is a very strong form of convergence. Intuitively, what happens on an event of probability 0 is often not that important in probability theory. So we will strive for a weaker notion of convergence where the sequence of random variables converges pointwise, but perhaps only on a set of outcomes that has probability 1. This brings us to the concept of almost sure statements. A statement is said to hold almost surely abbreviated a dot S dot if there exists an event which we might call the exception set N belonging to our sigma algebra script F such that this exception set has probability 0, that is P of N equals 0. And the statement holds true for all outcomes omega that are not in this exception set N. Let's consider an example. Two random variables X and Y defined on the same probability space omega script F P are said to be equal almost surely if the following exception set N defined as the set of outcomes omega in omega where X of omega is not equal to Y of omega, and this set N must be in our sigma algebra script F has a probability measure of 0, that is P of N equals 0. In such a case, Y is called a version of X, and this establishes an equivalence class of almost surely equal random variables.
Next, an example of almost sure monotonicity. Two random variables X and Y defined on the probability space omega script F P are said to satisfy X is less than or equal to Y almost surely if the exception set N defined as the set of outcomes omega in omega where X of omega is strictly greater than Y of omega and N is in script F has a probability measure P of N equals 0.
Now let's formally define almost sure convergence. A random sequence X mapping omega to the space of real valued sequences R upper N defined on the probability space omega script F P converges almost surely if the following exception set N has 0 probability. This set N is defined as the set of outcomes omega in omega where the limit inferior as N approaches infinity of X sub N of omega is strictly less then the limit superior as n approaches infinity of x sub n of omega, or where the limit superior as n approaches infinity of x sub n of omega is infinity. This set n must be in script f. If this condition holds, let x infinity be the point-wise limit of the sequence of random variables x on the complement of n, that is on n superscript c. Then we say that the sequence x converges almost surely to x infinity, and we denote this as the limit as n goes to infinity of x sub n equals x infinity almost surely. Let's look at an example of convergence almost surely, but not everywhere. Consider the probability space given by the interval 0 to 1 with the Borel sigma algebra on 0 to 1 and the Lebesgue measure lambda, such that lambda of an interval a to b is b minus a for all 0 less than or equal to a less than or equal to b less than or equal to 1. For each natural number n, we define a scaled indicator random variable x sub n mapping omega to the set 0 or 1 such that x sub n of omega is defined as n times the indicator function of the interval from 0 to 1 over n evaluated at omega. Let n be the set containing only the point 0. Then for any omega not in n, so for any omega strictly greater than 0, there exists a natural number m equal to the ceiling of 1 over omega, such that for all n greater than m, we have x sub n of omega equals 0. That is, the limit as n goes to infinity of x sub n is 0, almost surely, since the Lebesgue measure of the exception set n, which is just the point 0, is 0. However, note that x sub n evaluated at 0 is equal to n for all natural numbers n, so it does not converge at that single point. Now let's introduce another type of convergence, convergence in probability. A random sequence x mapping omega to R upper n defined on the probability space omega script f p converges in probability to a random variable x infinity mapping omega to R if the limit as n goes to infinity of the probability of a sub n of epsilon equals 0 for any epsilon greater than 0. Here, a sub n of epsilon is defined as the set of outcomes omega in omega such that the absolute difference between x sub n of omega and x infinity of omega is greater than epsilon, and this set a sub n of epsilon must be in our sigma algebra script f. As a reminder, convergence in probability, often denoted as limit x sub n equals x infinity ip, is a weaker convergence than almost sure convergence. It merely requires that the probability of the difference x sub n of omega minus x infinity of omega being non-trivial, meaning greater than epsilon, becomes small as n increases. Another reminder, limit x sub n equals x infinity almost surely means that for almost all outcomes omega, the actual difference x sub n of omega minus x infinity of omega gets small and stays small for large enough n. Let's see an example of convergence in probability, but not almost surely. Consider the same probability space, the interval 0 to 1 with the Borel sigma algebra and Lebesgue measure. For each natural number k, we consider the sequence S sub k equals the sum of I from 1 to k, the kth triangular number, and define integer intervals I sub k as the set from S sub k minus 1 plus 1 up to S sub k. Clearly, these intervals I sub k for k natural numbers partition the natural numbers, and the length or cardinality of I sub k is k. It follows that each natural number n lies in some unique interval I sub k sub n, such that n can be written as S sub k sub n minus 1 plus I sub n for some I sub n between 1 and k sub n. Therefore, for each natural number n, we define an indicator random variable x sub n mapping omega to 0 or 1, such that x sub n of omega is the indicator of the interval from I sub n minus 1 over k sub n to I sub n over k sub n evaluated at omega. For any omega in the interval 0 to 1, we have x sub n of omega equals 1 for infinitely many values of n, because there will be infinitely many pairs I, k such that omega falls into the interval I minus 1 over k to I over k. Hence, the limit superior as n goes to infinity of x sub n of omega is 1, which implies that the limit of x sub n of omega is not 0 for any omega. However, the limit as n goes to infinity of x sub n of omega is 0 in probability. This is because the probability that x sub n of omega is not 0, which means x sub n of omega is 1, is the length of the interval, which is 1 over k sub n. As n goes to infinity, k sub n also goes to infinity. So the limit as n goes to infinity of lambda of the set, where x sub n of omega is not 0, is the limit as n goes to infinity of 1 over k sub n, which is 0. Now let's discuss concepts related to infinitely often and all but finitely many events. Here's a lemma. Let A be a sequence of events in script f to the n. Part A, the event limit superior of a sub n, often written as a sub n IO. For infinitely often is the set of outcomes omega in omega, such that omega is in a sub k sub n for all n in n, for some subsequence k sub n that depends on omega. This is also equivalent to the set of omegas for which the sum over n in n of the indicator of a sub n of omega is infinity. This is precisely the set where a sub n occurs infinitely often. Part B, the event limit inferior of a sub n is the set of outcomes omega in omega such that there exists a finite n0 of omega depending on omega, for which omega is in a sub n for all n greater than or equal to this n0 of omega. This is equivalent to the set of omegas where the sum over n in n of the indicator of a sub n complement of omega is finite. This is precisely the set where a sub n occurs for all but finitely many n. Let's look at the proof. Let A be a sequence of events. For part A, let omega be in the limit superior of a sub n, which is the intersection over n in n of the union over k greater than or equal to n of a sub k. This means omega is in the union over k greater than or equal to n of a sub k for all n in n. Therefore, for each n in n, there exists some k sub n which is greater than or equal to n, such that omega is in a sub k sub n. This implies that the sum over j in n of indicator A sub j of omega is greater than or equal to the sum over n in n of indicator A sub k sub n of omega, which must be infinity, since omega is in infinitely many distinct A sub k sub n. Conversely, if the sum over j in n of indicator A sub j of omega is infinity, then for each n in n, there must exist some k sub n greater than or equal to n, such that omega is in A sub k sub n. If not, the sum would be finite. This implies that omega is in the union over k greater than or equal to n of A sub k for all n in n, which means omega is in the limit superior of A sub n. For part B, let omega be in the limit inferior of A sub n, which is the union over n in n of the intersection over k greater than or equal to n of A sub k. This means there exists some n0 of omega such that omega is in A sub k for all k greater than or equal to that n0 of omega. This directly implies that omega is in A sub k for all but finitely many k, which means A sub k complement occurs only finitely often. So the sum of indicators of A sub k complement is finite. Conversely, if the sum over j in n of indicator A sub j complement of omega is finite, this means A sub j complement occurs only finitely many times. Thus, there exists an n0 of omega such that for all n greater than or equal to n0, a sub n complement does not occur, meaning a sub n does occur. This implies omega is in the intersection over k greater than or equal to n0 of A sub k, and thus in the limit inferior of A sub n. Now a theorem. Convergence almost surely implies convergence in probability. If a sequence of random variables x mapping omega to R upper n defined on a probability space converges almost surely to a random variable x infinity mapping omega to R, then it also converges in probability to the same random variable x infinity. Let's prove this. Assume the limit as n goes to infinity of x sub n equals x infinity almost surely, and let epsilon be greater than 0. We define the events A sub n as the set of outcomes omega in omega, where the absolute difference between x sub n of omega and x infinity of omega is greater than epsilon for each n in n. We want to show that the limit as n goes to infinity of the probability of a sub n is 0. To this end, let n be the exception set for the almost sure convergence, that is, n is the set of omegas where the limit of x sub n of omega does not equal x infinity of omega, meaning lim in f xn is less than lim sup xn, or lim sup xn is infinite. We know p of n is 0. For any omega not in n, the sequence x sub n of omega converges to x infinity of omega. This means there exists an n0 of omega such that the absolute difference between x sub n of omega and x infinity of omega is less than or equal to epsilon for all n greater than or equal to that n0. This means that for omega not in n, omega is in A sub n complement for all n greater than or equal to n0 of omega. Hence, the set n complement is a subset of the limit inferior of A sub n complement. it follows that the probability of the limit inferior of A sub n complement is 1. Since the limit inferior of A sub n complement is the complement of the limit superior of A sub n, we get that the probability of the limit superior of A sub n is 0. The probability of a limit superior is the limit of the probability of the union from k greater than or equal to n of A sub k. This limit is greater than or equal to the limit as n goes to infinity of the probability of A sub n, which itself is greater than or equal to 0. Since the overall limit is 0, it forces the limit as n goes to infinity of p of A sub n to be 0.
Next, the Borel-Cantelli lemma. Let A be a sequence of events in script f to the n such that the sum over n in n of the probability of A sub n is less than infinity, meaning the series of probabilities converges. Then the probability that A sub n occurs infinitely often is 0.
For the proof, we can write the probability of a sub n occurring infinitely often, which is p of lim sup A sub n, using the continuity of probability and sub-additivity as the limit as n goes to infinity of the probability of the union from k greater than or equal to n of A sub k. This is less than or equal to the limit as n goes to infinity of the sum from k greater than or equal to n of p of A sub k. Since the sum over all n of p of A sub n converges, the tail sum limit as n goes to infinity of sum k greater than or equal to np of A sub k must be 0. Thus, p of A sub n IO is 0. Now, for the Borel 0-1 law, sometimes called the second Borel-Cantelli lemma, let A be a sequence of independent events, then the probability that A sub n occurs infinitely often is 0 if and only if the sum of p of A sub n is less than infinity, and it's 1 if and only if the sum of p of A sub n is infinity. Let's prove this. Let A be a sequence of independent events. From the first Borel-Cantelli lemma, if the sum of p of A sub n is less than infinity, then the probability of A sub n occurring infinitely often is 0. Conversely, suppose the sum of p of A sub n is infinity. This implies that the tail sum from k greater than or equal to n of p of A sub k is also infinity for all n in n. From the definition of limit superior and limit inferior, the continuity of probability and the independence of the sequence of events A, we can write the probability of A sub n IO as 1 minus the probability of lim sup A sub n complement, which is 1 minus p of lim inf A sub n complement. This is 1 minus the limit as n goes to infinity of the limit as m goes to infinity of p of the intersection from k equals n to m of A sub k complement. Due to independence, this is 1 minus the limit as n goes to infinity of the limit as m goes to infinity of the product from k equals n to m of 1 minus p of A sub k. Since 1 minus x is less than or equal to e to the minus x for all real x from the above equation, the continuity of the exponential function and our hypothesis that the sum of p of A sub k diverges, we get that 1 is greater than or equal to P of A sub NIO, which is greater than or equal to 1 minus the limit as n goes to infinity, limit as m goes to infinity of e to the power minus sum from k equals n to m of p of sub k. This becomes 1 minus the limit as n goes to infinity of e to the power minus sum from k greater than or equal to n of p of a sub k. Since the sum p of a sub k from k greater than or equal to n is infinity, e to the minus infinity is 0. So the expression is 1 minus 0, which is 1. Thus, p of a sub NIO is 1. Let's see an example where convergence in probability can imply almost sure convergence. Consider a random Bernoulli sequence X, mapping omega to the set 0, 1 to the n, defined on our probability space, such that the probability that x sub n equals 1 is p sub n for all n in n. Note that this sequence of random variables is not assumed to be independent and definitely not identical. If the limit as n goes to infinity of p sub n is 0, then we can see that the limit as n goes to infinity of x sub n is 0 in probability. In addition, if the sum over n in n of p sub n is less than infinity, then the limit as n goes to infinity of x sub n is 0 almost surely. To see this, we define the event a sub n as the set where x sub n equals 1, which is in script f for each n in n. Then applying the first Borel-Cantelli lemma to this sequence of events A, since the sum of p of a sub n, which is sum of p sub n, is less than infinity, p of a sub n IO is 0. This means p of lim sup a sub n is 0. Then 1 equals the probability of the complement of lim sup a sub n, which is p of lim in f a sub n complement. This means that for outcomes omega in lim in f a sub n complement, x sub n of omega is 0 for all but finitely many n, implying almost sure convergence to 0. Here's an important theorem. If a random sequence x mapping omega to R upper n converges to a random variable x infinity in probability, then there exists a subsequence n sub k for k in NA subset of natural numbers such that the sequence x sub n sub k for k in n converges almost surely to x infinity. For the proof, letting n sub 1 equal 1, we define the following subsequence and events recursively for each j in n. We define n sub j as the infimum of the set of n greater than n sub j minus 1, such that the probability of the set where absolute x sub r minus x infinity is greater than 2 to the minus j is less than 2 to the minus j for all r greater than or equal to n. And we define the event a sub j as the set where absolute x sub n sub j plus 1 minus x infinity is greater than 2 to the minus j. From this construction, we have that the limit as k goes to infinity of n sub k is infinity, and the probability of a sub j is less than 2 to the minus j for each j in n. Therefore, the sum over k in n of p of a sub k is less than the sum of 2 to the minus k, which is finite. It's a geometric series. Hence, by the Borel-Cantelli lemma, the probability of the limit superior of a sub k as k goes to infinity is 0. let n equal this limit superior of a sub k. This is our exception set. For any outcome omega not in n, it means omega is in a sub k for only finitely many j. This implies that for all but finitely many j in n, the absolute difference x sub n sub j of omega minus x infinity of omega is less than or equal to 2 to the minus j. That is, for all omega not in n, the limit as j goes to infinity of x sub n sub j of omega is x infinity of omega, showing almost sure convergence of the subsequence. And another related theorem, a random sequence x converges to a random variable x infinity in probability if and only if each subsequence x sub n sub k contains a further subsequence x sub n sub k sub j that converges almost surely to x infinity. As an appendix, let's briefly review limits of sequences. For any real valued sequence A in R upper n, we can define the limit superior of a sub n as the infimum over n of the supremum over k greater than or equal to n of a sub k, and the limit inferior of a sub n is defined as the supremum over n of the infimum over k greater than or equal to n of a sub k. As a reminder, we can define E sub n as the supremum over k greater than or equal to n of a sub k, and f sub n as the infimum over k greater than or equal to n of a sub. We observe that f sub n is less than or equal to a sub k for all k greater than or equal to n. This means that f sub 1, f sub 2, up to f sub n minus 1 are all less than or equal to a sub n. This statement seems slightly off. It should relate fn to ak for k greater than or equal to n. More precisely, f sub n is non-decreasing and E sub n is non-increasing. It follows that the supremum over n of f sub n is less than or equal to the supremum over k greater than or equal to any fixed n of a sub k, which is E sub n. And therefore, the limit inferior of a sub n, which is sup f sub n, is less than or equal to the infimum over n of E sub n, which is lim sup a sub n. A sequence A in Rn is said to converge if its limit superior equals its limit inferior. The limit denoted a sub infinity or limit of a sub n is then this common value. A theorem states a sequence A in R upper n converges to a sub infinity in R if for all epsilon greater than 0 there exists an integer n in the natural numbers such that for all n greater than or equal to n, the absolute difference between a sub n and a sub infinity is less than epsilon. For the proof, let epsilon be greater than 0 and find the integer n sub epsilon such that a sub n is in the interval from a sub infinity minus epsilon to a sub infinity plus epsilon for all n greater than or equal to n sub epsilon. It follows that a sub infinity minus epsilon is less than or equal to f sub n, the infimum from n onwards, which is less than or equal to E sub n, the supremum from n onwards, which is less than or equal to a sub infinity plus epsilon for all n greater than or equal to n sub epsilon. Hence, a sub infinity minus epsilon is less than or equal to the limit inferior of a sub n, which is less than or equal to the limit superior of a sub n, which is less than or equal to a sub infinity plus epsilon. Since epsilon was arbitrary, it follows that the limit of a sub n is a sub infinity. Finally, a proposition regarding sequences of non-negative real numbers. For any sequence A in R plus to the n non-negative terms, the following statements are true. Part 1. If the sum over n in n of a sub n is less than infinity, the series converges. Then the limit as n goes to infinity of the tail sum from k greater than or equal to n of a sub k is 0. Part 2. If the sum over n in n of a sub n is infinity, the series diverges. Then the tail sum from k greater than or equal to n of a sub k is infinity for all n in n. For the proof, we observe that the sequence of partial sums, sum k less than n of a sub k for n in n, is a non-decreasing sequence. Hence, its limit as n goes to infinity is the supremum over n of these partial sums, which is simply the sum of the series sum n in n of a sub n. For part 1, it follows that the tail sum k greater than or equal to n of a sub k can be written as the total sum minus the partial sum k less than n of a sub. As n goes to infinity, the partial sum approaches the total sum. If the total sum is finite, the tail sum, a finite value minus a value approaching it, is a non-increasing sequence with limit 0. For part 2, we can write the total sum as the sum of terms k less than n plus the sum of terms k greater than or equal to n. Since the first term, the partial sum up to n minus 1 is finite for any given n. If the total sum is infinite, it must follow that the second term, the tail sum from n onwards, must be infinite for all n in n. This concludes our discussion on almost sure convergence, convergence in probability and related lemmas. This is a very useful concept and we will reference it in further lectures as well.